Okay, let me just write down the two fundamental formulas that we used. So, okay, the one for the Coulomb force between nodes I and J. Which was at the end some constant beta, which represents the charges of the two particles, times, okay, it should be divided by the square of their distances, so xi minus xj squared. So this is the modulo of the force. To get the direction, we take the unit vector in the same direction. So it's, let's see, it's again xi minus xj, and we divide one more time by the size of the vector, of the difference. So this way, you see, if suppose that xj is in the 0 position, and xi, suppose that xi is in the 0 position, is in the origin of the axis, and xj is somewhere here with positive coordinates, this difference will be negative, which is fine because we want the force to be repulsive. So the sign should be correct like this. The second kind of force that we are using is the hook force between I and J, given by the spring, and it has a proportionality constant K, and then it depends on the difference between the distance from between xi and xj, and the ideal distance between the two, and this must be multiplied by the unit vector. In this case, we want it to be attractive when they are far apart. So when this is positive, we want it to be attractive. So I need to put here xj minus xi divided by the norm. So these are the two forces that we will use. About the signs, we will see probably. Okay, let me do this. Let's always write xj minus xi. So this becomes negative. Here xj minus xi. Of course, inside the norm, the order does not matter. So here the force will be attractive when the elongation of the spring is larger than its medial distance. So it should work this way. Next, of course, I would like to see the evolution of the system as it works. So, I would like to write a script that actually opens a window and draws the objects in it as long as they move in our space. Everything we will do is in R2, of course, on the plane. So to do this, we can use the tkinter package, which is an interface with the tk programming language, which has a GUI, a graphical user interface management code. So that, for example, we can create the root window by simply calling the tk method. See, this way we create a window, a root window for our application. And then we can, for example, it's an event-driven interface. So the idea is that you create you set up your window, and then you call the main loop function, and everything will be managed by events. So you need to provide functions and callbacks for the events you are interested in. But this code should create should simply create a window on the screen, okay? Which is what I want. Now, of course, we want to do something with this window. We want to draw something in it. So the next step is to add a component within the window that allows you to place drawing elements. And the element is called a canvas. And you can create it simply like this. Okay. So you create a canvas element and you place it within the root window. So it becomes a child of the root window. Next, you need your canvas to take the dimension of the window, so you cut it. In this way, okay, actually there is no difference from before. Probably the window is slightly larger. Let's do this. We add a width property. Height property, and also maybe a background color. Okay, this way the window should accommodate for a 500 by 500 pixel square region. Okay, which is what we get. Okay, so now what I want to do is place some balls in the window and observe them while they move. Maybe we can first experiment with placing one ball in the center of the screen. So what I do is, well, actually, I don't remember. Okay, so we want to create an oval object. So I call the create oval method, and okay, all that I need to place here are the coordinates of the bounding box of this oval. Suppose that I want to place it in the center of my 500 by 500 canvas. Let's give it a radius of 5. So it should be 495, 500, sorry, 245, because I want it at the center. And maybe let's use the fill property to have a color for it. Okay, so we fill it with the red color. Okay, so we have our ball in the center. Now the problem is that we also want to move those balls, and the idea is that when you create something in your canvas, it has its own ID, which you can use for further instructions to move it, for example. So now suppose that we want to take the ball and, I don't know, just to test the system before working on the spring model, we want to move it to random positions on the screen, maybe once per second. So the idea is that you create a function, let's call it move, for example. The name is not important, which creates a new random position for the oval. Of course, I need to import the random package. And then, for example, let's say new x position will be random.rand int from 0 to 499, which is bounding the limit of our visible canvas. Same for the new y coordinate, and then we want to modify the coordinates of the object ID to the new position. Of course, as before, I have to declare the bounding box, so it will be new x minus 5, new y minus 5, new x plus 5, new y plus 5. Okay, next I want this function to be called 1 time per second.
Oh, so
Please?
just new. Instead of units.
Okay.
And also the same.
Also the right. So either the X key is not very sensitive to that. I need to push it stronger. Next, I have to create an event which is fired every second by the system. It's a timer event, and let's see. Here, the function should be after. But okay, let me try to remember it without. So I want, after 100 milliseconds, the move function to be called. So the system will generate a timer event after 1000 milliseconds, and within this main loop, the move function will be called. Actually, this after function works just once. The event is fired just once, it's not a repeating timer. So I need to iterate the call every time it's fired. Okay. So every time the move function will fire a new event after 1 second. Okay. So the function is not called. So I get a problem in this function. Let's see how it's called. Accords. Okay. So now we should see the ball jump in random position once per second. Of course, we can make it much faster. Let's do it every millisecond. So the ball won't really jump once per millisecond. Probably it will take a little more, but because it does not make 1000 frames per second, of course. But anyway, by placing it at 1 millisecond, we get it as fast as we can. Okay, are you all okay with this? So does it work? Okay, now we need to start working with the spring system. So we start with our balls in random position, and you should remember we also need to keep track of the particle speeds, which will be initially 0. So let's use this code to create the window and to create the canvas within the window. Now, let me call X the list of particle coordinates, which is initially empty, and V the corresponding list of velocity vectors. Maybe here at the beginning let's set M, so the number of particles, to 4. So now we want to place, no, white for. Actually, rather than the number of particles, we should set the distance matrix of our particles. So, I would like to reproduce for example, the example of yesterday, which was 3 particles of mutual distance 1, and the 4th particle with distance 1 from the third. So 1, 2, 3, and 4, like this. In this case, the distance matrix should be 0, 1, 1, 0, because point 1 is connected to points 2 and 3. The matrix will be, of course, symmetric, and with zeros on the diagonal. 2 is connected to 3, and 3 to 2, and not to 4, and then 3 is connected to 4. So it should be like this. So let's just write down the matrix. Well, just another point. Let's take all coordinates in 0, 1. Okay, so all coordinates that we create here are real numbers between 0 and 1, and then when we want to plot them on our 500 by 500 canvas, we will multiply them. So here so 1 is too large, let's say 0.3, okay, as a distance between 2 points. 0. Okay, so we have the symmetric distance matrix between all pairs of elements. So we have a total of 8 non-zero entries, which are the 4 visible springs in that model. So that now we can define the number of elements simply as the length of the list D. D has 4 elements in this case. And now we need to create M different objects. So let's call it xi, the coordinates of the ith element. It will be a list of 2 random numbers from between 0 and 1. We can also create the, well, no, not necessary. And then, of course, we want to append it to the list of all coordinates. For the same reason, we want to append the zero vector to the list of velocities, so that we now have two separate lists of coordinates and velocities, which are initialized as required there. Okay. Now, now we have to create also all the ovals related to the elements. So let me retrieve this. Let's also create a list of IDs for our ovals. So the ID of every time we create an oval and we append its ID on the list of IDs. Where should we create the oval? Well, I can create it at arbitrary coordinates like this. Oh, sorry, probably can't see it very well. And then, after creating it, I move it to the correct coordinates. I prefer to do it with the convenience function. Let me put it up here somewhere. Maybe here. Let's define a function to move the ith oval in its position. So I have to call canvas.chords of the IDs of I object. And as for the coordinates, let's compute them here. The new x coordinate of the object will be the first coordinate of the object times 500. Then maybe we can also convert it to an integral. Same for the y coordinate. So I just need to take this and move it here like this. Okay, so we have a convenient function that only requires the order, the index of the IDs vector to move actually the oval. So here I can call move oval I. Okay, so I create an oval and I put it in the correct starting position. Of course, here the move function will completely change. Okay, so with this code, we should find 4 points initially scattered through our canvas.
But I think we should like divide it, because otherwise we get out of the screen if we just multiply by 500 the coordinate.
Divide by?
Like divide all the sides of our window each time and take the rest of the like use the page. Because if we multiply coordinates every time, we just negate now the window.
No, we are not changing the coordinates.
Oh.
So these coordinates for the moment remain fixed. I'm just taking them and putting only here they will appear multiplied by 500 because I want them spread on the 500 by 500 object canvas, but then I just remultiply them every time. But anyway, let's check. I'm never sure of what I'm doing. Okay, so here we have 4 scattered points. Of course, now comes the hard part. We also want them to move. So everything else now will be done in the move function. So here, now, in the move function, okay, we need all the logic for computing the forces and so on. Okay, maybe we can do it by degrees. We can define a function that provides the Coulomb force between balls placed in 2 coordinates xi and xj. Okay, how can we do it? Well, first we need to compute the vector with the difference of the 2. So let's call it dx will be the difference along the first axis. So it will be xj 0 minus xi 0. And dy will be the difference along the second axis. So xj 1 minus xi 1. Then we need well, the distance, yes, which is, we need to take the square root of dx times dx plus dy times dy. What do we need next? So we want to compute the Coulomb force, but nothing else. Just need to return. So the first component of the force will be the constant beta, which we will define later, times dx divided by ds times ds times ds. Same for the y component, for the second component of the force. and it should be same if we want to define the hook force. Well, they are names, so let me put the capital initial letter between objects in position xi and xj. To compute the hook force between two objects, I also need to know the appropriate dij distance. So the rest length of the spring. As before, I need to compute these numbers. Let me just copy and paste the code to compute the relevant vectors. So now let's say the difference in length is the distance between the 2 points and the rest length of the spring. So now let's just return the k constant times the difference in length times the first component of the vector divided by the size of the vector, and the same thing on the dy part. Okay, a lot of things can be pre-calculated. I'm computing them twice. So, well, let me just slightly optimize this. Here, for example, I can use the s squared in the Coulomb force like this. The y times the y. And here I put the s squared. So here I can create an overall constant which is beta divided by ds squared times ds, which is the cube of ds, beta. So here I can remove the two computations like this. Also here I can compute the constant as k times dl divided by ds. Okay, so I avoid unnecessary computations. I do them once and for all. Okay, now that we have the forces, please.
I think we have not divided on 3 times dx, ds in the direction.
It's here.
Oh, okay, yeah, okay.
Now, okay, now we need to actually move our balls. So first, okay, so we just need a loop m times now we need to maintain a force which we will call F. So let's say the two components of the force that acts on element I will be initially 0, and then for every other element J, we will add the force that J exerts on I. And the force will be a Coulomb force if J is not connected to I, or a Hooke force if it's connected. So for all objects J, of course, if J is equal to I, then we skip the step. Otherwise, we can have two cases. Either I and J are connected or not. So let's take Dij which is actually the distance between I and J, which is in the matrix. Sorry, I'm always in the low part of the screen. So I'm here now. D was the matrix like that. I assumed that 0 means don't care. Okay. Of course, we never need a needle distance of 0. If 2 points have the needle distance of 0, then we would treat them as the same point. Now, if Dij is 0, then the 2 points are not connected, and we want to apply the Coulomb force on them. So let's take the Coulomb force between the ith coordinates in our list X and the jth coordinates in the same list. Otherwise, the force between, let's call it Fij. Fij will be the Hooke force between xi and xj with ideal distance dij. In both cases, we have to add the force to the overall force Fx and Fy for our node. So Fx is incremented by Fij 0 and Fy is incremented by Fij 1. After we have iterated, on all j's, so after we have terminated this loop, Fx and Fy will contain the overall force acting on element I. So now, as you remember, the force will modify the velocity of the node. So we just need to change the velocity of node I. So the first component of velocity of node I will be the previous value plus some proportionality constant, which is the mass of the element, times the x component of the force then everything will be multiplied by a damping factor, which represents viscosity that tends to break the node. Same for the second component, like this. Now, after we have updated all speeds of all nodes, we use those speeds to update the position of the nodes. So, another loop for I in the same range. We simply take the position of node I, and we use, oh sorry, here I also need the time increment, delta t. Okay, so mass times force times step. And also here I want to increase x with the same component of the velocity of the node times the time increment. I do the same for the second component, 1. Then I use the new coordinates to move the oval at index I. So the function move oval will use the vector x to place the oval at the new coordinates. And we should be done, apart from a few details. For example, here I have deleted the call to the first iteration of the move. Okay, this is to start everything after 1 millisecond after we start the main loop. We start calling the move function. Then what we are missing, and let me put it up here, are the constants. Here we need to be a little creative. So alpha, which is the mass of the particles, well, let's say it's 1. Beta, which is the charge of the particles, let's assume that it's much smaller, 0.001. Then we will calibrate. As I told you yesterday, the algorithm is rather sensitive to parameters. So we need to play with them to see what happens. Then we have the elasticity constant, let's say it's 1. It's much more important than the repulsion constant. Next we have the viscosity. Let's take a number close to 1, which means that velocity is slightly reduced at every step. But there is we want to keep a lot of inertia in the movements. And finally, the time increment, let's say 0.01. And let's see what happens. Probably some error message. In fact, I forgot to import the map package. Oh, there is some stray y instead of what is it? Okay, in the hook force here I have written y instead of dy. Okay, now it works. Well, it doesn't work exactly as I hoped. Oh. Okay, it's not exactly what I wanted. Probably I inverted the sign of some force, because probably the Coulomb force is in the wrong position. Well, this is an interesting behavior, but it's not what I actually wanted. Actually, what I wanted to see was for the system to take a shape and then stay with it. Let me see if it was just a problem with the Coulomb force. So we can either look at the code and think about it, or simply try inverting a few variables and see what happens. So let's say, let me invert the Coulomb force. Well, it's much better. This is the behavior that I wanted. In fact, you see, the system goes precisely in the shape that we expected. So I assume that this is node 3 and the others are a consequence. Maybe we can put labels on the nodes. Well, before putting labels, let's play with the parameters. For example, now the system is frictionless. Okay, eta is 1 means that the force is never reduced. What happens in this case? In this case, you see, the system oscillates. The balls are never forced to take a position. There is nothing that breaks them, that halts them. So they keep bouncing around. They are never losing energy. We want the system to lose kinetic energy because we want it to obtain a fixed position at the end. So is that clear why eta equal to 1 does that? Because we are only working with conservative forces, forces that have a potential. So the energy remains the same. And so kinetic energy will never fall to 0. Let's operate with a very viscous system. Okay, now eta is 0.5. Now balls are moving in a medium which resists their movement a lot. So actually, you don't see them moving almost. They try to reach their position. They will eventually reach their position, but it will take time. So let's remain with 0.99. Another point, what happens if we set beta to 0? Beta is the repulsion. So beta equal to 0 means we don't want, we only look at Hooke's forces and we don't consider repulsive forces. So what now happens is that the system reaches a position, but you see, as far as I understand, these are points 1, 2, and 3. Probably this is point 3, and this is point 4. Point 4 has no reason to move in the opposite position, because it feels no repulsion from these nodes. If we rerun the program, we will have another configuration again. 1, 2, and 3 are an equilateral triangle, but node 4 is not repulsed by this node and remains here instead of moving on the other side. Maybe we could really try putting some text on the, but no, because it takes time. Okay, let's remain with beta. So let's keep these parameters: alpha equal to 1, beta equal to 1000, and so on. Let's try to see what happens with a much more complex graph. And the graph that I propose is, well, maybe a 5 by 5 grid. So, I want 25 nodes connected by horizontal and vertical springs. Okay, so let's build the matrix, which will have 25 nodes in this case. So I'm going to comment this. Of course, I don't want to build the matrix by hand, so let's write a little code to create it. So we start with an empty matrix D. Let's say that we want 5 rows and 5 columns. And then, okay, let's fill the matrix. So, I want to create n rows by n columns rows in the matrix. Let's say the column of element I will be the index I modulo the number of columns. The row of element I is I divided by the number of columns. And its connection, and we need to determine its connection with the generic element J in the same range. So that the column of element J and the row of element J are determined in the same way. here we're in the internal loop, we're going to create one row of the matrix D, let's call it dr. And then, it's similar to what we have done last time to create the self-organizing map network of 3 by 3 elements. So we want to connect two elements if they are on the same row and their column differs by 1, or they are in the same column and the row differs by 1. So if Ci is equal to Cj and Ri is equal to Rj minus 1, or Ri is equal to Rj plus 1, so they are in the same column and their rows differ by 1, or same thing but with rows and columns inverted. So every R becomes a C, and every C becomes an R. If this happens, then we append a non-zero value to dr, let's say 0.1. We want everything to stay to be in a 0,1 by 0,1 rectangle. Else, we append 0. Finally, out of the for loop, we append to D the row that we have just created. Okay, this way we should have that kind of grid. Let me see what happens. Okay, apparently it works. Okay, so what happened here? Well, in this case, it worked quite well. Let's try a few times. I never set a random seed, so it will be different every time. You see that sometimes the system finds it difficult to evolve. It tends to, and probably if we insist long enough, we will find a case where it doesn't work. Well, I would like it not to work now, please. Okay, maybe that's it. Oh, no. No, it works. Okay, how not to make it work? Let's just reduce eta. Let's put it 0.95. In this case, reducing eta means that the particles are encouraged to stay where they are, not to keep their speed. We reduce their inertia. So now maybe, but only maybe, no. Okay, I encourage you to try with different parameters. What can happen actually is that the system gets stuck in some so-called local minimum. One possible case is this. Maybe because of how the particles were set, at a certain point we end up with this kind of connection. So maybe one half of the network is reversed with respect to the other half. Of course, in this case, it's difficult for the system to reverse everything, because it would require to overcome the repulsion between many particles. So the system can actually end up in some sort of local minimum, of local optimum. We're not always guaranteed that this well-spread network will happen. Anyway, let me go back to eta equal to 0.99 so that the system evolves in a reasonable time. Okay, it works. You see, probably something like this happened. And in fact, you see that probably this is attracted by this. There is a spring between here and here, and so on. Here in this zone, the springs are reversed. But there are too many repulsions between the particles to reverse everything. So it remains in this state. What we can do here is, by the way, let's look what happens if we remove repulsion. Okay. Why? Because something similar to what I told you yesterday about the square is happening. Now, if we only care about distances between first neighbors, then this grid has no reason to stay this way. We should fold it in half, and it would work exactly the same way. Okay, we only matter about this length. So, if you look at this, you would probably find that all points that are connected to each other have actually distance equal to 1. They simply have no reason of moving far apart from each other. So in this case, we really need the Coulomb repulsion. Okay. Maybe now I should add a few lines to make it work better. How can we do it? Well, okay. After creating all the elements, let's create a new list which will contain the line IDs. And let's put a line for every pair of connected objects. So if the distance between I and J is not 0, then we should draw a line between I and J.
So it should be X range or just range?
Oh, thank you. Actually, it's the same. I prefer X range because it creates dynamically the least one. Thank you. Okay. So I want to create a line a line will have a list of endpoints, but let me put it at 0, 0 initially. Then I will create a function move line which places it where we want. So we append this line to the line ID. And we need to move the line to the appropriate endpoints. So the line ID must be moved between points xi and xj. So all that I need now is to define the function move line, which will be somehow similar to the move oval, but actually requires the ID of the line and the two coordinates of the endpoints. So the new x of the first endpoint will be integer of xi of 0 times 500. You see that in this case I pass the coordinates and not just the index, because, well, it's probably easier this way. 2.1, 2. Oh, well, actually, I don't even need to place them on variables. Just say canvas chords of the object ID, which represents a line, will be this. That should be all. Okay, then here, after moving all ovals, in the move function, okay, the one that makes all the movements, at the end, I want to do something like this. So for I and j that vary here, I simply want I need a way to count the lines, so that I is initially equal to 0. Here the ID that I'm using is the Lith element of line IDs, and then here I increase Li, okay? Consider that not all pairs of points have a line between them. So I need to take line IDs precisely in the same order as before. This should do the trick. I forgot the column here. Okay, so now we see actually what happens with the grid. And we can also see a little better what happens if we, for example, remove repulsion. Okay, so you see many all springs have length 1, but the network is folded onto itself many times. We can see it better if we reduce the number of rows and columns to 2, so that we actually have a square. If you have a square, then you see, in this case, so the square was folded in half, and these 2 points are close because they don't feel repulsion among them. The unfolded version should be more or less a perfect square. In fact, if you run the version without repulsion many times, you should find many different configurations. You see that when the square is folded, then 2 nodes will always coincide with their position, precisely because they need to have the same distance from the other 2 nodes. You can also see what happens with the larger networks, maybe 10 by 10. I just reduce by half the distance. Of course, the Python script becomes a little slower because it's working on many more nodes, 100 nodes. But given enough time, you see that now there are many springs that have a very large stress, they are much more elongated than they would like to. But actually, in fact, in this case, with so many nodes, it seems that the Coulomb repulsion is too strong. In fact, nodes tend to remain too far apart from each other. So probably to make this work, you see that I expected the network to collapse, but actually nodes tend to stay far apart from each other. Probably because they feel too much repulsion from each other. So, in this case, probably we need to reduce, maybe let's divide it by 10, the charge, so the repulsion force between the nodes. At least in this case, the nodes will tend to remain on screen. They will still feel a bit of repulsion from each other, so maybe it's not enough repulsion to actually untangle the network. So see, this somehow proves that the system is very sensitive to parameters, which is not a good feature for an algorithm. But of course, we can think of a system with adaptive parameters. In this case, let's see what happens if we reduce the friction, the viscosity. So in this case, the system becomes much more bouncing, but actually the network is untangling. So given enough time, we should end up with, well, I'm not really sure. Let's reduce beta. Another observation is that, of course, here we are spending a lot of time to visualize the system after each step, which is not, of course, the case when you want to represent a graph. So, what I would do usually is, okay, repeat a lot of updating steps without visualizing, which would, of course, make it much faster. Okay. Anyway, yes, we have to play a lot with parameters before finding the ones that work in this case. Probably Coulomb repulsion is still too strong. Okay, anyway, if any of you finds a set of parameters that works well with the 10 by 10 network, let me know. Now, here I reduce it again to a 5 by 5. Still something that does not work. Oh, I forgot here. Okay, anyway, as usual, I will put this on the course web page. Okay, so you can see also some interesting examples of network tangling. Okay, if you don't have questions, then I think that for today the lesson is over. Maybe I will spend the next 10 minutes to put this on the web page so you can have a look at it.